Some discoveries feel small at first. A faint dip in a star's brightness. A whisper of gas drifting across a telescope's sensors. A signal so subtle that it takes weeks of analysis before anyone dares say what it might mean. But every so often, the universe delivers something that stops the scientific world completely, a signal that forces us to ask not whether life might exist somewhere out there, but whether we are already looking at it. 40 light-years from Earth, orbiting a cold, ancient red dwarf barely larger than Jupiter, lies a planet that has become the center of one of the greatest scientific debates of our time. TRAPPIST-1E. A rocky world sitting in the precise middle of its star's habitable zone, whose atmosphere has now been probed by the James Webb Space Telescope with a precision never before achieved. And what those layers of spectral data suggest is something that astronomers have barely dared to say aloud. For the first time, we may be looking at a world with every known ingredient for life. When scientists first turned their instruments toward the faint red ember known as TRAPPIST-1, no one expected much. It is an M8 class red dwarf, radiating at just 1/1800th the brightness of our Sun, dim, ancient, and unremarkable at first glance. But beneath its stillness lay something extraordinary. One by one, tiny dips appeared in its light. Planets, crossing in front of the star. And as the signals accumulated, astronomers realized they weren't looking at one habitable candidate, or even a handful. They had found an entire family, 7 rocky, Earth-sized worlds orbiting closer to their star than Mercury orbits ours. An entire solar system built to a different scale, around a different kind of fire. Most experts initially dismissed the system as hostile territory. Red dwarfs are notorious for violent magnetic storms and ferocious flares capable of stripping planetary atmospheres bare before life ever has a chance to take hold. But TRAPPIST-1E refused to be ruled out. It orbits in the exact center of its star's habitable zone, receiving roughly 2/3 of the light Earth receives from the Sun, enough to sustain liquid water, if, and only if, the planet can hold on to a stable atmosphere. That single condition became the driving force behind one of the most ambitious observational campaigns in the history of astronomy. And the instrument chosen to answer it would push the boundaries of what humanity has ever attempted. When NASA allocated early observation time on the James Webb Space Telescope, one team made their decision immediately. They aimed the most powerful telescope ever built directly at TRAPPIST-1E. Their goal was both simple and audacious: determine whether this small, distant world had an atmosphere at all. To do this, they employed transmission spectroscopy, a technique so delicate it works by measuring how a planet's atmosphere absorbs infinitesimal slices of starlight as the world passes in front of its star. For most exoplanets, the signal is too faint to be useful. But TRAPPIST-1 offered a rare advantage. Because the star is so dim, any transiting planet blocks an unusually large fraction of its light, producing a stronger spectral signature than would ever be visible around a Sun-like star. Webb recorded wavelengths across 4 separate transits of TRAPPIST-1E. And what came back was not noise, but information. Some possibilities were eliminated immediately. No primordial hydrogen-helium envelope, stellar radiation would have scoured that away long ago. No thick Venus-like carbon dioxide blanket. No thin, dying Martian wisp. All of these were ruled out. What remained was something far more compelling: the possibility of a nitrogen-dominated atmosphere with greenhouse contributors, water vapor, methane, carbon dioxide, in proportions that could support liquid water across the surface of a tidally locked world. An Earth-like atmosphere, 1 billion times more interesting than silence. That was the moment scientists first began to whisper, quietly and carefully, that this world might not just be habitable. It might be alive. But an atmosphere alone tells only part of the story, and the next part is deeply strange. TRAPPIST-1E is almost certainly tidally locked, one face permanently bathed in the red light of its star, the other frozen in endless night. This is not the Earth we know. It is a world divided. And the question that immediately follows is whether heat can move effectively enough between those two hemispheres to prevent catastrophic extremes from making the surface uninhabitable. Webb's data offers clues without yet providing certainty. If methane concentrations are high, an inverted greenhouse effect could cool the surface and confine liquid water to the dayside alone, not a global ocean, but a hemispherical sea, warm and lit beneath a rust-colored sky. Other models suggest something stranger still. Simulations have identified what researchers call Terminator habitability, a narrow ring of perpetual twilight circling the planet along the boundary between day and night. In this thin strip, winds driven by the temperature contrast between hemispheres could maintain stable, temperate conditions, a climate band unlike anything on Earth, where life would neither experience sunrise nor sunset but exist in an eternal, windswept dusk. Some calculations suggest it is narrow enough to fit inside a continent. Others suggest it could circle the entire globe. The difference between those two answers may be the difference between a barren world and a living one. And there is yet another possibility, one that requires us to look not at the surface, but beneath it. Tidal forces from TRAPPIST-1E's neighboring planets in the system constantly flex and squeeze the planet's interior, injecting internal heat at an estimated rate 24 times greater than Earth experiences from its own tidal forces. This process mirrors what happens on Io, Jupiter's innermost moon, the most volcanically active body in our solar system, a world whose interior is perpetually churned by the gravitational pull of its siblings. If TRAPPIST-1E experiences something similar, the result could be persistent volcanism, continuous replenishment of atmospheric gases, and liquid water maintained beneath an icy crust, a subsurface ocean, hidden from the star's fury, sealed from radiation, and potentially home to chemistry as complex as anything stirring in Earth's deep-sea hydrothermal vents. Life, in such an environment, would not need sunlight. It would need only heat, water, and time. And TRAPPIST-1E has all three in extraordinary abundance. The star itself remains the great paradox at the center of this story. TRAPPIST-1 is violent. The worst geomagnetic event in Earth's recorded history, the Carrington event of 1859, would be routine here, occurring roughly every 2 days. Charged particles would rain down on any nearby planet in a near-continuous bombardment, stripping atmospheric molecules one by one. By any simple reckoning, a planet this close to a star this temperamental should be a scorched, airless rock. And yet the very same ultraviolet radiation that threatens to destroy an atmosphere also played a critical role in forming RNA building blocks, the molecular foundations of every living thing we have ever studied. The violence that could erase life may also be the force that sparks it. TRAPPIST-1 is now in its calmer phase, its volcanic youth long past, its output significantly reduced. If TRAPPIST-1E developed a magnetic field, generated by a molten iron core and amplified by tidal heating, it may have held onto enough atmosphere during the star's quieter eons to arrive at this moment with something worth detecting. A world shaped by extremes. Not destroyed by them. And the data web has returned suggests that something, somehow, survived. Here is where the story becomes a cliffhanger in the most literal scientific sense. The spectral readings from TRAPPIST-1E are not clear. They are not the strong unmistakable signature of thick carbon dioxide, nor the obvious fingerprint of a primordial hydrogen envelope. They are faint, ambiguous, and precisely balanced on a razor's edge, consistent either with a truly airless world or with a dense, compact atmosphere dominated by heavy molecules that Webb is only just beginning to resolve from 40 light-years away. An Earth-like nitrogen atmosphere would leave exactly this kind of subtle signature. One that requires not a single observation, but a sustained campaign of accumulating evidence, transit by transit, until the noise floor drops low enough for truth to emerge. 15 additional transits have been scheduled. Each one refines the spectral fingerprint. Each one brings the data closer to a threshold where ambiguity collapses into certainty. If carbon dioxide, methane, or nitrogen appear with consistent signatures, it confirms a secondary atmosphere, a world that rebuilt itself after the chaos of its star's youth. If water vapor is detected in any measurable quantity, the implications could be historic in a way that is almost too large to hold in the mind. We may be months away from the first confirmation of life beyond Earth. Or from the realization that we came closer than any generation before us, and still fell short. TRAPPIST TRAPPIST-1 also confronts us with something that the human mind struggles to absorb: time at a scale that makes our own history invisible. Red dwarfs burn so slowly, so efficiently, that their total lifespan can reach 10 trillion years. The entire current age of the universe, 13.8 billion years, is barely a beginning by that measure. TRAPPIST-1 has already survived its dangerous infancy. What lies ahead for this system is a span of stable, gentle starlight so vast that life, if it exists there now, would have more time to evolve, adapt, and grow complex than anything on Earth will ever experience. The threat to life was in the distant past. The gift is an almost eternal future. That is the haunting paradox at the heart of this world. In the end, what TRAPPIST-1E offers us is not certainty, but weight. The weight of evidence that refuses to point away. An atmosphere that something, tidal heating, a magnetic field, volcanic replenishment, sheer geological resilience, may have preserved against all probability. A climate that, in multiple independent models, finds ways to remain stable even under tidal lock. A star that is both the greatest threat to life on this planet and possibly the very reason life could have started there at all. Every anomaly, every ambiguous spectral line, every model that finds a pathway to habitability adds another increment to a probability that is quietly becoming difficult to dismiss. We are not dealing with vague hints or theoretical abstractions. We are staring at a real, rocky, Earth-sized planet 40 light-years away, whose atmosphere may be within our ability to confirm in our own lifetimes. A world where chemistry could be stirring beneath red skies at this very moment. A world that may already have its own answer to the question we have been asking since the first human looked up at the stars and wondered if anything was looking back. The James Webb Space Telescope is still watching. The transits are still coming. And somewhere in the data that has not yet been collected, the most important sentence in the history of science may already be waiting to be read.